What if you're studying cancer in patients and you want to know which of 4 new treatments is most effective? Well, you'd use Anova, right? Right. But you'd also want to be careful that you aren't missing a continuous factor that might covary with your results, such as distance from a major source of pollution. Well, Anova won't model a continuous predictor variable because it only works for categorical variables. You need something more. Well, never fear, because analysis of covariance is here. Analysis of covariance techniques, or Ancova for short, can be used to address this very problem. Now, like Anova, analysis of covariance has a single continuous response variable, y. However, Ancova can have predictor variables that are both continuous, like in regression, and categorical, like in Anova. Well, but isn't this kind of like regression? Well, yes, in a sense. Ancova is sort of a blending of Anova and linear regression, in that we can model a continuous random variable with both continuous and categorical predictors. So as in a regression, we can model y in Ancova with both continuous and categorical independent variables. Now, we use Ancova when you have some categorical predictors and factors and some quantitative predictors. But unlike regression, the covariate variable in Ancova, well, it's not necessarily of primary interest. But when we include them in the model, we can actually explain more of the response variable and reduce the error variance. Now, in some situations, if we fail to include an important covariate, we can actually get misleading results. Let's do an example so you can see that. You and I have been hired by the American Cancer Institute, and they want us to study 4 potential treatments for esophageal cancer. Now, our response variable, the dependent variable, is going to be the number of months a patient lives after being placed on one of those 4 treatments. So we open their database and we notice they've got 12 patients with esophageal cancer. And so we place them in 4 groups of 3 each. Now let's analyze the data as a one-way ANOVA. Here, months is equal to the total number of months the patient survived post-treatment, and treat is equal to the one of 4 treatments, either 1, 2, 3, or 4. Now notice here we have a plot of the survival time post-treatment. Our x-axis has the 4 different types of treatments, treatment 1, 2, 3, and 4, and y has the survival time in months. So this analysis tells us that there's a significant treatment effect. Notice it suggests that treatment 1 is the best, since those people lived longer post-treatment. Let's walk through our code of how we did that in R. First, we said LM of our model is just LM of months on treatment. And then I want to do an ANOVA of that to get an analysis of variance table. Here's the response, my treatment, with degrees of freedom of 3, n-1 or 4 minus 1. And then you see my sum of squares, the mean square, my F statistic, and look at that super low p-value. So your ANOVA results confirm that your treatment levels are significant. Now we submit our analysis and we recommend treatment 1, but there's a problem. In fact, we actually didn't consider something in doing our initial analysis. Look at this plot of duration by treatment. So there's clearly a linear relationship between the duration of cancer in the body and the survival time post-treatment. Here's where we went wrong. The 3 patients in group 1, well, They've all had esophageal cancer for less than 5 years. And notice that 3 patients in Group 2 have had cancer between 5 and 9 years. Group 3's had cancer between 9 and 12 years, and Group 4, close to 15 years or more. So in our initial analysis, we didn't consider the stage to which the cancer had progressed by the time that treatment began. And now this is important because those who are at earlier stages of the disease, well, they're naturally going to live longer on average. In fact, the stage of disease is a covariate. So we should have been more intentional in using randomization to balance out our groups. Now, after seeing the survival time versus disease duration, it's clear that we can't compare the survival time without considering the prior duration of the disease. Survival time is affected by the number of years a person has had the disease or the stage of the disease. Now, cancer stage, that's a way of describing where the cancer is located in the body or where it's spread and whether it's affecting other parts of the body. So in this case, esophageal cancer actually occurs in 4 stages, and we didn't randomize our groups according to the stage of the disease in the body. Now, first, the stage of the disease is the contributing factor towards survival time. Survival really didn't have anything to do with the choice of treatment necessarily. It just happened that everyone on treatment 1 was also at an earlier stage of the disease, and so on. So it made it look like there was a larger treatment effect. In fact, what if we were to recommend any treatment at all, or we might recommend that we study the treatments more, but we might actually prefer to recommend treatment number 4. Because even though all of the 4 treatments were equally ineffective, treatment 4 was actually used on those who had the worst cancer stage. All right, let's include now the stage of cancer in years in our model and see how that changes our output. Here's our linear model, Model 2, and we're going to model months on years plus treatment. Let's look at Anova of our linear model. All right, notice here, we've got years and treatment as our response, and you see the associated degrees of freedom and the sum of squares and the mean square. Notice our F values, and more importantly, look at the p-value. Now, the p-value for treatment is actually still significant at the 5% level, although it's not significant at a 1% level. But notice the dominating factor in that model is years, the stage of cancer in the body, which has a very significant p-value. Now, while we're not directly interested in the number of years a person has had cancer, we needed to include it in our model, just as a covariate, because we failed to properly randomize. Now, let's randomize our patients according to their stages. We're going to take our same data, let's set dot seed of 1, 2, 3, 4. And now I'm going to take months 2, where that's equal to now a sample from my original vector with replace equals false. So that's telling R, I want to sample 12 times from this vector so that I split up where my data values occur. Likewise, for years, I'm going to sample from that vector to randomize where the years occur. Now notice here, once we randomize by stage, we have much more spread in the survival time post-treatment. There's not a clear treatment that outperforms all of the others. And notice here, each of our groups has a mix of patients in various stages of esophageal cancer. So by randomizing, we can eliminate the effect of cancer stage on treatment. Now, as you look at our Anova results, notice here, treatment is not even significant anymore. In fact, it's got a p-value of 0.8998. And notice, even when we add years back to the model, both of those variables remain insignificant. Look at our updated results. we've taken the linear model, model 5, as LM of months, the randomized months, on the randomized years plus treatment. And we've done an Anova of this call function. Our analysis of variance table gives us the months, the years, and the treatments, along with their degrees of freedom. So 1, 3, and 7 for the residuals. You see the associated sum of squares, 267.5 and 570.7. And then the mean square. Remember, that's just your sum of squares divided by the degrees of freedom. So 267.52 and 190.22. And then the calculated F statistic and the associated p-value. Now notice that both of those p-values are insignificant, much greater than 0.05. Now once we intentionally randomize our treatment by stage, we see that neither the treatment nor the stage of the cancer has any effect. Now, R is smart. It fits in Ancova whenever you have both categorical and continuous variables in your model. Now, suppose on the other hand, we wanted to model multiple dependent variables with our independent variables, like multiple Y variables. What would we do in that case? Well, you've actually seen this in the IRIS data set. Remember where we had 4 dependent variables and they each depended on 3 independent variables? Now, in a situation where you have multiple dependent response variables, you can test them simultaneously using a multivariate analysis of variance, also known as Manova. Now, a multivariate analysis of variance could be used to test that hypothesis. Hey, so let's look at how to keep straight the differences among Anova, Ancova, and Manova. But before we can appreciate the differences, it's beneficial to notice some of the similarities among them. Now, a multivariate Anova is an Anova with 2 or more continuous response variables, meaning I've got 2 or more Y variables. Now, like Anova, Manova has both a one-way and a two-way version. Now, the number of independent factor variables involved distinguish a one-way Manova from a two-way Manova. When we're comparing, say, 2 or more continuous response variables by a single factor, that's a one-way Manova. A two-way Manova, on the other hand, is going to also compare 2 or more continuous response variables, but is going to compare them by at least 2 independent factors. So Manova can be used in certain conditions. First, the dependent variables should be normally distributed within the group. Now, this R function called mShapiro.test, we can actually use that to perform the Shapiro-Wilk test for multivariate normality, which is going to be very useful in the case of Manova. Secondly, like Anova, Manova assumes homogeneity of variances across the range of our predictor variables. And Manova assumes linearity between all pairs of dependent variables and all pairs of covariates and all of our dependent variable covariate pairs. Now, if a global Manova test is significant, we would conclude that the corresponding effect, the treatment effect, is significant. And in that case, well, the next question is, we'd have to determine if the treatment affects only, say, the weight, or only the height, or both. In other words, we'd want to identify the specific variables that accounted for a significant global effect. All right, let's perform a Manova on our IRIS dataset. And we're going to use it to determine if there's any significant difference between the different species. Now, this is for sepal and petal length and width. And now, remember, species, that's our only independent variable. So this is a one-way Manova. All right, let's remember our iris data set. We have sepal length, sepal width, petal length, petal width, and species. Here you see a sampling of variables from our data set, and you see their associated values, along with the species, Setosa, versicolor, and virginica. Now, our first step in interpreting a Manova is side-by-side box plots. Because remember, we want to know that there's heterogeneity of our variance. So we can do a box plot of our iris data. This one is by sepal length and species. So notice the spread of those box plots. That's exactly what you want to see. You want to see a similar variability, and so you want the range to look approximately the same for each of those species across sepal length. You notice a couple of outliers, but none of them are going to take away from the fact that those are approximately equal variances. Let's look at the same for sepal width. Here you see side-by-side box plots for Setosa, versicolor, and virginica. And again, notice that's a nice range of your variance. Now, sepal length and sepal width have significant overlap among the groups. Let's see if petal length gives us a bit more separation. Here we see the box plot for petal length by species. Notice that there's a clear distinction between Setosa and versicolor and virginica, and that versicolor and virginica have a bit more overlap. Notice also that the variability of Setosa is slightly less than the other two. So this is something we'd actually have to take into account when we do our Manova to make sure that our results will be valid. And here again, we see the box plot of petal width by species. Likewise, Setosa stands apart. There's some overlap in virginica and versicolor, but the ranges of those two in terms of their variability are roughly equivalent. Now, as the graph suggests, box plots for the measurements show that versicolor and virginica are more similar to each other than Setosa. But let's fit a multivariate one-way Anova to model this iris data set. Here's how we do that in R. First, we have to load the library mass. And then from mass, we want to pull out the iris data set, which is contained inside. And then let's attach that data set. So first, my Manova model, or ManMod, is going to be equal to Manova. So R has a Manova function, which does a multivariate analysis of variance. And I'm going to do a columbine of sepal length and petal length. So I want sepal length and petal length as my Y, and I'm going to model that with my independent variable species. Here are the results from our Manova output. Now, notice we get the terms. This is the first response, response 1, the second response, response 2, and the degrees of freedom. So in our case, our responses were sepal length and petal length. And then you see the associated species to those responses. So species for response 1 gets a value of 63.21, and species for response 2 gets a value of 437.1028. And you see the associated residuals. Now, this isn't really the best way to look at the output. In fact, it's better to look at a summary of your Manova model. So let's do summary of ManMod so we can actually see if there's significance. Now notice in this output, we get our species with 2 degrees of freedom, and we get a Pili value. So Pili is just one method of doing a multivariate ANOVA. There's actually 4 different methods, but this is the default. R gives us an approximate F value and associated degrees of freedom, and then notice our P value, which tells us that species is significant and is significant relative to sepal length and petal length. Now, if we actually wanted to go further, we could do a summary.AOV of our Manova model. This is actually going to tell us the response by petal length and sepal length. Let's look at that output. So here we've called summary.AOV of man.mod. Notice the first gives us the response for sepal length. It tells us the associated degrees of freedom and the sum of squares, and then the mean square of 31.6, our F value, 119, and then an associated p-value, which says, yeah, this is pretty significant. But now compare it to the output that you get for petal length. Again, 2 degrees of freedom, but look how those sum of squares jump to 437.1. So what does that mean? Well, petal length actually is capturing more of the variability, right? I'm able to use petal length to better distinguish between species. Notice the mean square and look at that F value, 1,180.2. I mean, that's way out in the rejection region. Compared to the F value for sepal length was only 119. Now, both of those are significant, but petal length is giving you more information about species, hence the very large F value that you see. Now we can actually do a Manova on all 4 of our variables. Here you see we've done a Manova on a columbine of sepal length, sepal width, petal length, and petal width. Now I could do a summary.AOV to look at each of those. And I mostly want to draw your attention to the F value because they're all going to be significant. But that F value is really telling you where the strongest variables are most significant. Here's the first one for sepal length. Notice we have an F value of 119.3 and is significant. Now notice what we get for sepal width. Ooh, our F value actually goes down to 49.16. Now, this is actually confirming what we noticed in those box plots. Remember, for sepal length and sepal width, it was harder for us to discern the species because there was so much more overlap. Now check out petal length. There's that high F value that we saw before, 1,180, because it does a better job of separating by species. And likewise here, we see for petal width, has a high F value of 960, because likewise, those box plots do a great job of separating the species for us. Now R has a cool data set on skulls. And these are skulls that were found in Egypt belonging to 5 different epochs in 4000 BC, 3300 BC, 1850 BC, 200 BC, and 150 AD. I know you're excited to look at some skull data set. So let's say we wanted to know if the measurements changed over time, since maybe a non-constant measurement might reveal that there was possible interbreeding outside populations. Okay, so we're going to evaluate this hypothesis test. The null hypothesis is that the pattern of skull measurements does not differ across epochs, so across those different times. The alternative is that the pattern does differ across epochs. Now we can use Anova to discover whether skull measurements vary most across epochs. Here's our data. First, MB is the maximum breadth of the skull. BH is the height from the jaw top to the top of the head. BL is the length of the skull from behind the jaw to just below the nose. And NH is our nasal height. So these are the 5 measurements that we have for that data set. Now in R, we first have to load the library HSAUR because this is where the skulls data set lives. So load that library and then call the skulls data set with data of skulls. And then let's look at a summary statistic. So summary of skulls. Notice that gives us our epochs. So each of our times in BC, the 4 BC times and the 1 AD time. And notice that for each of those times, we have 30 data points. And here you see the range of MB from 119 to 148 with an average of 134. BH from 120 to 145 with an average of 132.5. BL ranges from 81 to 114 with an average of 96.46. NH range from a minimum of 44 to a maximum of 60 with a mean of 50.93. Let's fit a Manova model to our skulls dataset. First, we're going to call it sk.mod, or skulls model. It's going to be a linear model where we combine, columbine or cbind, MB, BH, BL, and NH. So these are my 4 Y variables. And I want to look at that relative to epoch, which is our year, from the data of skulls. And now we want to do a Manova on sk.mod. Notice the output that we get, a type 2 Manova, where that default is the Pillai test statistic. We've got 4 degrees of freedom, and you see our test statistic, 0.35 approximately, along with an F value, 3.512, the degrees of freedom, 16, and look at that super low p-value, 4.67 times 10 to the minus 6, suggesting that each of those is significant. Now we can always do a summary of our Manova, and what's interesting to bring up here is the diagonal, because along the diagonal, you actually have the sum of squares for each of your variables. So for the first one, our sum of squares is 3,061. For BH, the sum of squares would be 3,405, and so on. Now, when we've collected data from, say, a medical experiment, where the response variable is Y is the recovery time in weeks, and let's say our explanatory variables, X1 is gender, and X2 is systolic blood pressure, tell me what would you use? Anova, Ancova, or Manova? Did you say Ancova? You'd be right, because in this case, we have only one continuous Y variable, and we have both a continuous and a categorical X1 and X2. Here's another example. Let's say we've collected data from a medical experiment where now the response Y is recovery time in weeks, and our explanatory variables are X1 equals gender, X2 equals race, and X3 equals treatment. What would you use in that case? Anova, Ancova, or Manova? Did you say Anova? You'd be right again, because now we've got one continuous Y variable, and each of our X's are all categorical. Okay, here's another example. You've recorded the effect of 3 new methods of laser eye surgery, and you want to determine if vision differs for either the left or the right eye. So you model your response Y as Y1 is the visual acuity in the right eye, Y2 is the visual acuity in the left eye. And our explanatory variables, X1 is laser surgery 1, X2 is laser surgery 2, and X3 is laser surgery 3. Now, which one would you use? Anova, Ancova, or Manova? Well, hopefully you guessed Manova here, because notice we've got 2 continuous Y variables, and we've got categorical X1s, X2, and X3. All right, one more. You've been hired to determine the unemployment rate for the city of Los Angeles. You decide to model the response variable Y as unemployment rate, and your explanatory variables are X1 equals to the district, X2 is race, X3 is level of education, and X4 is population size. What would you use in this case? Anova, Ancova, or Manova? Well, hopefully you said Ancova, because here we have a single continuous Y, but we've got both categorical and continuous predictor X variables. So remember, analysis of covariance is an extension of Anova. that can statistically control the linear effect of continuous variables that you don't want to examine in a study. Now, Ancova allows researchers to remove the effects of some previous continuous variable in studies where maybe direct experimental methods aren't available to control for those variables. Manova, on the other hand, extends Anova to compare 3 or more means. Now, compared with doing multiple rounds of Anova separately, Manova is actually more likely to uncover real differences and avoid fake differences, especially those type 1 errors. But there's a possible pitfall. Manova is not always better. For instance, if your dependent variables are correlated, the independent variable would appear more important than it actually is. You should use Anova instead. And Manova can be complicated. You need to sort through which independent variable is affecting each dependent variable. Now, R is smarter than us on a bad day. So even if we tell it to do a linear model, but we really need to do an Ancova, well, R is going to do the correct model for us. But we still need to check normality conditions using Shapiro-Wilk or the multivariate Shapiro-Wilk. Now, Ancova and Manova are powerful, but they're also even more sensitive to violations of the assumptions from basic Anova. Well, in our next lecture, we'll get to see how Anova works with experimental design.